Where I come from, the mother tongue that I speak, there's a saying, "Undavanukku thondum thondavanukku unnuvadum mayakam." So essentially, even for irrespective of whether somebody is in the labor class or the management, everybody after food they feel sleepy. But I'm really glad so much of boisterous interaction you all are having. I hope I don't dampen that with the class. You were saying something?
Just wait 15 minutes. let the effects kick in.
Sure.
The carbon pile.
Right. Okay, so as we said, we are going to use this more as a reference, but just for you to cross-check, I had the chapters list. But something that for those of you who are interested would want to take a look at, nothing to do with this particular course or its assignments, whatever, but just to see what is the parallel between life and the dynamics that we study of bodies and particles. There's a beautiful book which is a translation of a book which was originally written in 600 BCE. So that's almost like 2600 years old book, but the original was in Sanskrit, and this is a English translation. There have been many English translations in between, mostly by philosophers, but this one is a little more interesting for us engineers because Professor Subhash Kak is at the University of Oklahoma, is professor of computer science and electronics over there, and he has done a beautiful job in terms of interpreting it and from the Western physics point of view. So it's very interesting. Now, if you remember when I was discussing various things, I brought in the concept of the frame of reference. So the frame of reference is very important in order to take derivatives of vectors, I said. Okay, you have to specify the frame of reference. Now, the frame of reference is only one aspect about what we call as an observer. So essentially, when we are doing a dynamics problem, we are observers. We are looking at some motion of a set of particles and or rigid bodies, and we are trying to mathematically model that, and we know a few things. In terms of those knowns, we want to solve for the unknowns by using certain set of equations, of which Newton's laws are a very, very important part, especially the second law. Now, when we do that, the frame of reference plays an important role because you essentially are observing from that frame. We talked about the aircraft fixed frame, we talked about the earth fixed frame, and I was using the letter I because I stands for inertia or inertial as well. So inertial frame of reference is a concept we will introduce shortly. Essentially, it's a frame which is not accelerating itself. So if there is a frame which is not accelerating itself, then the Newton's law is valid there. So in other words, whenever you are using a frame of reference which is non-inertial, Newton's laws, the way I wrote it, the second law, F is equal to ma, or the rotational equivalent of that, which is torque T equal to I omega, they are not valid. And the funny part is that there's no such thing as an inertial frame of reference. In reality, we were taking Earth as a frame of reference, but you know that the Earth is rotating about its own axis and revolving around the Sun. So it's essentially a rotational motion, and whenever there's a rotational motion, even if the speed doesn't change, which it does in the case of the Earth, even if the speed doesn't change in a circular orbit, for example, if it were not an elliptical orbit, just by virtue of the fact that it is rotating and revolving, there is an acceleration because the direction of motion is changing. Remember that velocity is a vector, it is speed along with a particular direction, and either the speed changes or the direction changes or both change, there is going to be an acceleration. And if the frame itself is accelerating, obviously your Newton's laws are not valid. But what comes to the rescue is in terms of the relativity, in terms of not relativity in the sense of Einstein's relativity, but essentially we're talking of the relative nature between the speeds that we are talking about for the aircraft, the speeds we are talking about the Earth, the size, etc. Yeah.
So does that mean in dynamics, are we going to be taking, or are we going to be considering things outside of the system also in calculations, or are we still kind of going off of the principle that anything outside of a certain system has such a microscopic, like a small impact on the system, so we don't have to consider it? Like what?
Absolutely, a really very good question there, because in reality everything is correlated with everything else. It's a question of how strong is that correlation, or how strong is the interaction effect, right? As you said, most of these are negligible. So there's no point in beating around the bush trying to take everything to get change in your result in, let's say, the 14th or 15th decimal point, right? So there's absolutely no point. So what we really do is we identify what is the major effects, and therefore, as you pointed out, without using that word, we are looking at an isolated system. So where we are not taking into account those external impacts or influences which are anyway going to cause negligible effect.
So
But
still a system surrounding.
absolutely. And that brings me to another important point. Typically in dynamics, whether it is what we are talking about, the way dynamics as part of mechanics, we call it engineering dynamics. But in your own study in Georgia Tech, you'll look at thermodynamics, you look at aerodynamics. So they're also having dynamics aspects to it. But there's one is having heat flow, the other is having a fluid flow, right? So all of these things, typically there are two approaches which are typically used to understand this. So I'm really glad you're asking these kinds of questions, because these will bring in certain subtle aspects of what we are doing, which might otherwise not come through in my lectures. So there are two approaches when you undertake a model, and that is, one is you are moving along with the object that you are interested in. For example, you're trying to do the let's say the aircraft dynamics, you're moving along with the aircraft and you are only interested what's happening to the aircraft, not with the air which flows past it, because the air which flows past it at this instant is very different from the air that will flow past it in just a few seconds later, right? It's an entire new set of molecules that are traversing on the surface of the aircraft. On the other hand, there are certain things called where you're having the control volume and you're trying to track what is happening at a particular location, irrespective of what is flowing across it. So you just hold your volume in space with respect to, let's say, the Earth, and then you are seeing whatever molecules are passing through it, what is happening to it. So these two different approaches eventually should give you the same result, but for the right reasons, this is something which is more preferred by the fluid dynamicist, the thermodynamicist, whereas this is more preferred by the structural engineer. But it's not necessarily necessary to bifurcate in those ways, especially when you're looking at fluid structure interaction problems, etc. You might use either one of those approaches and you'll be modeling both the fluid and the structure. One is this, remember, a gaseous material, the other is a solid material. So we could do that. So, but in either case, the whole idea is that we have to focus on what we are interested in. In one case, we are interested in what's happening to the aircraft. The other case, it's a fluid flow, aerodynamics or thermodynamics. We are interested in what's happening to the fluid which is flowing. Then we are tracking that. So it all depends on that. So as long as you know what your primary interest in, what you're going to calculate eventually, you choose the right kind of approach. But in either one of them, obviously you will take only the major influences. You will drop off that which is going to cause a negligible effect because it's not going to be of much help, right? So this particular book, though it's written just about 5-10 years back at the most, you see that the original source, which was in Sanskrit, this is essentially a translation and an exposition or a commentary on that, was in Sanskrit. That is the Vaisheshika Sutra, and the original author is Kanada. So Kanada is a person who really understood it from a very, very fundamental perspective, because not only did he look at the dynamics in all the details that we talked about, kinetics, kinematics, rigid bodies, particles, etc., and the Newton's laws that you are familiar with from high school, of which we only took up the second law so far. He also went into not just stating those laws, but what is the proposition behind it, because of which this came. Whereas in the 1687 work, which Newton came up with, he directly stated those laws without giving the propositions or how the logic behind arguing it out is. So this will give you a very, very different perspective, because it also gives you from the observer's perspective, not purely as a frame of reference, because as I said, the word frame of or phrase frame of reference and rigid body can be interchangeably used for a lot of things. Like we talked about the earth fixed frame, so that's a frame as well as earth is a body. Similarly, a aircraft fixed reference frame, it's a frame of reference as well as aircraft is a body, right? So you interchangeably use. But when you talk of frame of reference, it's not just the physicality. As a human being, when we are the observer, we are not just the physical body, we are the mind as well. So that plays a huge critical role in terms of how the problem is analyzed, how it is modeled, and that's where we are not just frames of reference, but also the consciousness plays an important role. There's a whole lot of studies on consciousness in many physics and science departments around the world in the topmost universities, because we will shortly see the whole whatever spectrum of physics that is, and how much we really know and how much we don't know, and a lot of which we don't know can actually be accessed once you start looking at the observer not only as a frame of reference but also as a consciousness which is built into it. Okay, so these are things beyond the scope of this particular course. I'm only giving you a briefing because today is the overview of the course, so just trying to put the things into perspective, where we stand as a body of knowledge today and what are the possibilities, especially if you're thinking of doing fundamental research in physics, the directions in which you could go for a better understanding. Because classical mechanics already has been beaten down the bush in terms of very high speeds, what we call as the theories of relativity, both special and general, and at very small particle sizes, which we're talking about as quantum physics, right? So it's not that these are sacrosanct, holy things that we have to always believe in, whether it's the Newton's laws or the classical physics or Einstein's laws in the theory of relativity, or you're looking at let's say quantum mechanics, the principles of uncertainty by Heisenberg, etc. None of these are like written down in a way that it cannot be violated. There is a range of validity, a huge range of validity, because of which engineering is possible the way it is today. All of these technologies that we are using, your laptops, mobile phones, the aircraft, the lightings that we have, the fans that we have, air conditioning, even the buildings, none of these would have been possible but for a lot of this classical mechanics, Newtonian based mechanics. But there's a whole large universe beyond that, which is almost 95% of the universe, which most physicists talk in terms of the dark matter, dark energy, etc., which are not amenable either to classical physics or to relativistic physics or to quantum physics. And you really need to go beyond that, and which is what people are trying to do. So for us engineers, it's okay because we are working in a very, very limited field. But if you're looking at it from a much more fundamental human understanding of science, then we need to go beyond, and consciousness is the key. And a lot of the Sanskrit literature, including this, I'm bringing this particular one out of thousands of Sanskrit literature, because this is purely about physical sciences, and the physical sciences are understood from the observer's perspective, not only as a frame of reference but also as consciousness. Okay, coming back to what we are doing in this particular course, we are taking advantage of just 8 of you being there, right? 8 of you crediting the course, and therefore it's a relatively small class compared to what typically is in a dynamics course. So we want to not do things the way it is routinely done for this kind of course, but at the same time we want to ensure whatever learning takes place in a typical course, but we want to take it a level beyond that, which is why it is designed this particular way. So this picture is of course to show you that this is not the way this course is going to be evaluated, or you are not going to be evaluated like this little guy here. Neither am I looking like that, at least from the hair's perspective. So coming to the evaluation, what is the basis on which we will be evaluating? There will be no exams, as I already told you in the email. All of them will be assignments, and it's not written submissions. You will have oral presentations based on whatever problems you're going to be working out on, and you will come and make presentations either using slides or the whiteboard over here, or combination of that, to come up with the solutions for a few problems that we will give. And all of these will be team contributions. You will not be evaluated as individuals. I really want each of you to help each other because each of us have certain capabilities, certain skills, certain talents. We come from various different backgrounds. We want to see how we can help each other out, because that's the way industry works today. I'm sorry to say, but we come from two of the best institutions, Georgia Tech and IISc. But when I talk to some of the industry people, whether in India or abroad, especially in the US, a lot of them keep complaining about the kind of students that they get to their jobs. Even after all the interviews, the training period is much longer than what they would ideally like, because they want to put them on the job as quickly as possible, and they are not ready for it. And the reasons for that is essentially, one is in terms of the way things are being understood is still the way people were understanding 100 to 150 years back, especially things like dynamics. But there's, with the advent of computers, with the advent of software, with the way things are being modeled today, the focus should be more on the formulation of the problem rather than the solution of the problem. Most people, most textbooks as well as lecturers are focusing still on the solution methodologies for simple problems which are not even realistic. In the real world, you have like hundreds of thousands of degrees of freedom, huge problem sets, and these are being solved on a routine basis using computer systems. And so there's no real advantage of doing hundreds of problems in terms of the solution. What is more important is to be having the skill set to model realistic problems. The problem formulation is half the problem solved, because once you have put it in a mathematical model, then the solution process can typically be taken over. And even the recent past, let's say last 2-3 years, the way AI and LLMs have progressed, a lot of this problem formulation is also being taken over by the automated systems, the computational systems. So where the real focus is in terms of the way we ask the questions to these LLMs, for example, because there's a whole branch of engineering called prompt engineering which is coming up, where you're essentially trying to understand how to prompt these LLMs, whatever state they are in right now, to minimize the hallucinations that they go through and get all kinds of garbage. So if you have a way in which you can improvise your prompts to get better and better responses, which are more utilizable as they are, then I think that's the way to go, which is why I want you to use all these tool sets. A lot of professors are against the use of these things because they think that learning will not happen, etc. They have their own obvious concerns. Some of them are reasonable, but more often than not, all of technology is a dual-edged sword. You can either use it or you can misuse it. Same is true right from the simplest thing like a knife. In the hands of a murderer, it can be used disastrously. In the hands of a surgeon, it can be used to make somebody who's about to die live longer, right? So it's the identity that I take when I'm using the tool which makes the tool itself useful or not useful. It's not the tool per se which we should criticize or we should praise beyond limits, right? So that's the way in which I want you to utilize some of these modern tools, and we will see how these go by. The reason why I'm stressing on this is I'm going to give you exact same homeworks which I gave to the previous batch. The same, I'm not even going to change the numbers over there. And you have the video recordings of those guys presenting it. And they were a brilliant batch. I can't say that much about the structural analysis group last year. This year's was much better, I hope. But even with dynamics, even though I had some of the most brilliant students in that batch, I want at least a few of you to show beyond that brilliance. And since this is teamwork, that brilliance will rub off on the rest of the group as well. And that's precisely what I'm trying to look at. Yes, Tila?
How will the team be structured?
It's not one team versus another team. It's the same.
Oh, is it the entire class?
Yeah.
Oh, I see.
Yeah.
I thought it would be
Yeah.
like a pair or something.
No. All 8 of you. So you're not, see, the whole idea is not competing with each other. You're trying to help each other out. Not even one team versus another team, but all 8 of you. Okay, so as I said, the way in which we have to learn, and this is more true when I'm teaching a graduate level course, because the students go through some of the colleges where the teachers themselves do not understand what they're talking about, right? So we get some of these, we have a program in our Indian Institute of Science called the quality improvement program, where some of these lecturers who are just at the master's level come here to do PhD with us. When we interview them, one of the first questions I used to ask in the beginning was, what subjects do you teach? So that they get into their comfort zone and try to ask some fundamental questions related to that. But over the few years that I was here in IIC in the beginning of my career, I found out that that's a really dangerous thing to do, because they just don't know the fundamentals of what they are teaching. You might as well ask about areas in which they are not teaching. They might be better at that. That's the level. If the people who are teaching are at that level, you can understand how the people who are learning from them will be. Okay, so that's the very important thing, that a lot of the students have learned without their own intention certain not so correct things. I'm not saying wrong things, but things which are kind of dicey, based on some assumptions which are not valid. They may not be necessary, they may not be relevant. Some of these assumptions make the results and the process, the derivation, either inferior or not usable at all. So I really want those things to be unlearned, whereas in an undergraduate class we're mostly coming fresh from school. Most of those fundamentals are still valid, so we will not need to do too much of that. But that is not enough, right? So once you have unlearned what is not so correct, you want to learn. Again, I'm not telling it is the correct thing, because what I teach you today might be questioned probably tomorrow in terms of the body of knowledge developing, because how we understand the universe is evolving, and what I'm presenting is what is the current state of the art as I understand what I have learned from my teachers and or my experience working with real life problems in the industry. So I would like you to give a flavor of that, so that you learn the more correct than what you already know, so that there's a value addition in your whole learning process. But the last thing is the most important thing, where you then apply it to the problems in your homeworks and try to see how you can apply that assimilated knowledge and see how best we can not only solve and get to the number or numerical result of that problem, but more importantly understand what is the whole purpose behind giving you that problem. Okay, so what is the learning that you get out of solving that problem? It's not learning that happens only through the lectures. Learning happens through the homeworks and the way you present the homeworks also. So I want you to give me the takeaways, not only the assumptions you make to get to the result, but also the takeaways in terms of how you, that knowledge that you have assimilated, how you can apply it to more real life problems. So these are the things that I would really like you to test. Are there any questions about the grade, the way we grade and the takeaways right now, or if you have questions later also you can ask about it. Okay, so if you're fine, let's go forward. Okay, so now for the first assignment. Now that we know what the grading is all about, is the first assignment, and we want to start off light. So this is a story that most of us have learned as part of childhood. Either we have heard from our parents, grandparents, or friends, or we have read it ourselves in storybooks. Aesop was a great writer of fables, and one of the famous fables that he wrote was the Hare and the Tortoise, right? You know the simple story where the hare and the tortoise decided to race. The hare ran very fast. He looked behind, saw the tortoise is still way behind. He said, there's no point in me reaching now. Let me just take some rest. He took some rest. The rest continued for much longer than he intended. The tortoise overtook that location and reached the finishing spot. And very simplistically, the people who told that story to us said that the slow and steady win the race, right? That was the so-called moral of the story. But we know, as aerospace engineers, we are trying not to be slow, but to be as fast as we can. So obviously, steady is, of course, important there, but it's not necessary to be slow and steady. We could be fast and steady. Okay, so that's the next level to go to, and that's where there are 3 more episodes of this particular story. Anybody has heard the other episodes of this? Okay, good. So, of course, you would have, because I brought in the same story in the previous course that I taught as well, but from a different perspective of structural analysis there. But essentially, there are 3 more episodes to this. The second episode is when the hare realizes his mistake. Said, okay, I was lazy, in between I just took a break, which is why this happened. So let us go for the race again. This time the same path on which we raced earlier. So, and then the tortoise agrees to it, and then both of them run. The hare doesn't take a break. He wins the race. The fast and the steady wins the race, right? So that is one level of understanding what our limitations are, what our weaknesses are, like the hare did in terms of his laziness, taking a break unnecessarily, etc., or longer than necessary. Then he saw the result of that, and once he rectified that behavioral attitude, he could win the race. Then the tortoise didn't stop over there. He said, okay, now I understand this kind of a race he's always going to win. Let me change the path of the race. And then he decided on a new path for the race, and then he called the hare once again. He thought, oh God, this is really stupid of this guy. He wants me to race again, even though he knows that I'm not going to take a break in between, but he still went for the fun of it, and they both raced, right? So then the path was marked by the tortoise. Of course, the hare didn't know the path, and as the hare ran very fast, he reached half the path, and he saw that there's a river, and he didn't know swimming. The tortoise came very slowly much later. Then he swam across, and then he reached the finishing spot, which was on the other bank of the river, right? So then you hear what you're trying to do is to understand your strengths. The previous thing, you understood your weakness and limitation and try to rectify that. Now you understand your strength, and you're trying to play to your strengths and bring that strength as part of the game. Okay, so you're changing the game rules to make the game much more broader. It still involves that road path, which is the path in which the hare is strong, but it also involves the path where only the tortoise could succeed. So that's what happened. Then they decided, by this time they had 3 races, and so they'd become very close friends. So they decided, let's do this again. This time we will do it as a team. And what happened is they could do it both much faster, because the first half the hare carried the tortoise on his back and ran through the land. And once the water was reached, it was the same path. So the tortoise took the hare on his back, and he finished the race. So overall, as a team, they could perform much better. So this is what holds for the assignments that you would have also. So you guys have known each other for a while now, so you know your strengths and weaknesses, at least of your own, if not the others. So then bring your strengths to the party as far as the team is concerned, and let's see how best you can perform. And now that you also already have the same set of homeworks being solved by the previous batch, you can look through that and also see how you can do it even better, because they all got it the right solutions. So it's not just getting to that number which is important, it's the process, the procedure. Just as they say, it's not the destination alone which is important, it's how you get to the destination is also important. So it's that I want you to see how you bring in the assumptions, what are the takeaways beyond the problem. Having already solved that simple problem, the way you have solved it, can it be taken forward to some realistic problems? So I want you to think aloud about it when you make the presentations. So let me just give this in a perspective that one of the perspectives that I thought about it in a hurry. So you might be able to think about it in much better way. So let me go through this. Okay. So many of us have heard this fable. So the first line itself was like most fables, it starts with once upon a time. Okay. And once upon a time, you're already introducing that concept of time, which is most fundamental, critical to the dynamics, right? And also in terms of the way we pose a lot of the dynamics problem as initial value problem, then it's not only the governing equations which are important, but the initial condition also. So we are saying at a particular point in time what happened. So if we know that, then we can kind of extrapolate and find out based on the behavioral attitudes of the hare and the tortoise what could happen later. So that's the initial condition. We are talking about a dynamical system also. One is we know the attributes of the dynamical system in terms of its behavior, like the mass matrix we saw, the inertia matrix we saw. So we know the tendency of that, how it's going to, the motion is going to pan out, right? So now in order to be able to solve it, we should also know what is the starting point. That is where the initial condition comes in an initial value problem. Next, we are introducing the characters of the story. Once upon a time, the tortoise and the hare, right? So the tortoise and the hare, you can think of in this particular case for the dynamics kind of an application as idealized rigid bodies, okay? So two bodies, of course, the hare is not as rigid as you might think. The tortoise shell might be reasonably rigid, but essentially, since our course AE2220 is talking about only rigid bodies, I'm trying to correlate with that, and we think of these two as two rigid bodies, okay, ideally speaking. And also, to start with, we are thinking of them as unconnected, and which means that we are introducing another concept from dynamics, which we will study a little more detail as we go in the future classes, is about constraints. We talk of what are known as holonomic constraints, non-holonomic constraints, rheonomic, scleronomic constraints, etc. All of these will play a huge role in terms of the solution process of the problem, because it's not just the governing equations, but subject to what conditions, and those conditions are expressed in the form of constraints. So right now we are thinking of them as two separate entities, the hare and the tortoise, which means that they are unconnected. In other words, unconstrained problem is what we are starting with. Now, what do they, even before they talk about the race, first of all, there's an argument between them, right? So that argument is essentially setting up what they're trying to find out. What they're trying to find out is who is faster amongst them. So essentially trying to identify a particular skill set that they're looking at, which means we start exploring in a dynamics problem a certain feasible space. So we look at a certain feasible, just like in any mathematics problem, you don't search all over the place. Because of the constraints that are involved, we have a certain space. Even if there are no constraints based on the very problem definition, maybe the solutions can be only real numbers. They cannot be imaginary or complex numbers. So then you already have limited field to search from. That helps the whole solution process to be more efficient. So that's the argument you're talking about. Let's say it's a feasible solution space. Now the next thing that what they were arguing about, right? Who is faster? That is what they want to determine. So from the point of view of dynamics, what the entity we already introduced was time. The second entity was the constraints. The third that we are talking about now is we are talking about the speed, which is the magnitude of the velocity. And we are looking at the who is having a larger magnitude of the velocity or larger speed, and which means that it's the same velocity but without talking about a particular direction. So at this stage we are only looking at faster, okay? In other words, only the magnitude of that vector, not the direction of that vector. Next we or they rather, the hare and the tortoise decide on something. So essentially what's the decision making process when we are doing it is choosing the methodology. Remember, already in the short while that we've been discussing dynamics, we already talked about three methodologies: Newtonian, Lagrangian, Hamiltonian, without going into the details of the Lagrangian and Hamiltonian, of course, but we said that both of them are part of what we call as the work energy principle. Then we also talked about the impulse momentum principles. These are all three different overall categorization of methodologies. Within them there are again many different categories. So we can choose any one of those methods, and more often than not for the same problem many different methods might work. For example, if you're thinking of a pendulum problem, you could solve it using Newtonian mechanics. You could also solve it in Newtonian mechanics using Cartesian coordinates. You could solve it using let's say circular coordinates with r theta. Some of them might be more convenient, comfortable compared to the other, and it all depends upon the particular geometry that is involved, the motion that is involved. You might choose one over the other. So all of these again can be done. The simple pendulum problem can be done Newtonian mechanics, Lagrangian mechanics, Hamiltonian mechanics, impulse momentum method, etc. And the choice will depend upon what is going to be most efficient for that problem. Also, some of them might give you intermediate results which others might not, and that might be something that you're looking forward to. Then you choose that, right? But what do these two guys that we are talking about, hare and tortoise, decide? They want to settle what they were arguing about, that is who is faster. They want to find out by a particular methodology which they choose, which is the race that they want to have. And that race is essentially what we call in dynamics or in most of physics and science, as variational principles. So essentially you're coming to what is known as moving from calculus to calculus of variations. You're moving from what you dealt with as functions to functions of functions. Okay, one level more complex than what the problem that you're dealing with. And when you're doing that, either you are coming up with a minimum of a certain quantity or a maximum of a certain quantity, either globally or locally, what we in general call as a stationary principle. So essentially, like for example, if you want to find the maximum of a function f of x, you take the derivative df by dx, set it to 0, then you solve for x, and then you find d squared f by dx squared, find it whether it is positive or negative, and depending upon that you come up with minima or maxima, right? On the other hand, here we are dealing with functions of functions, and then we have what are known as variational principles, or principles of the stationary principles, and then there we need to do a little more involved derivation. We end up with a set of governing equations called the Euler-Lagrange equations, along with the boundary conditions, and then you solve a boundary value problem. In many of the dynamics problem, it will also be an initial value problem. Okay, now that you know the methodology, which is the variational principle, what you want to do is the specific route, because the same race can be run on many different routes. In fact, if we saw in episode going from episode 1 to 3, there was a change in the route. Okay, 1 and 2 were in a particular route, 3 and 4 episodes, the third and fourth episodes were in a different route, right? So you want to start off on a route, and obviously you have to agree with that. So that's where what is known as an initialization of the problem comes in, because most of these are nonlinear problems that we deal with, and you want to have an initiation to iterate. You may not be able to directly solve it. So then you have an initial guess to iterate upon, which is what that particular aspect of the story comes up. And then once this is done, you start the race. Okay, so you go about raising, which is essentially nothing but you have a chosen solution process. You have implemented it first as an algorithm, then as a code, and then you're running it on an operating system, and you come up with a solution, and that's essentially your solution process that has learned. And you which in the story analogy, of course, is they have started raising, right? Okay, the same episode we continue. The race has just started, so obviously one of them is much faster than the other in terms of its inherent characteristics. So some of the inherent characteristics of bodies we looked at already are the mass matrix and the inertia matrix. Somebody who's light probably can, keeping all other things the same, can probably run faster than somebody who is heavier. So there are certain things that are inherently the characteristics of the person or the body or the particle that we are dealing with, based on which certain possibilities are there. But here we are talking about what happens to start with, and therefore you're talking of the so-called initial velocity. Okay, so then this hare sprints some distance or time, as we already saw in the episode, but he takes rest there, right? That sprinting for some distance is essentially what we will introduce a little later, much later in the course, as a concept called generalized speeds. Okay, by generalized speeds, like just when we talked about in the morning generalized forces, we said torques and moments are also generalized forces. When we talk about generalized speeds, we introduce the concept of angular velocity. So those angular speeds are also part of speeds. They have different units. The speeds that we talk about typically are the translational speeds of meter per second, whereas the angular speeds are in radians per second. They might be looking like different kinds of entities, apples and oranges, but at the end of the day they are both fruits, right? So same way here we are talking of whether it's angular speed or translational speed, they're all generalized speeds, and that's something that we need to take into account over there. The next thing is once the hare has gone a certain distance, not the finishing line, but somewhere in between, it cognizes its huge lead over the tortoise, right? Which means that you typically do this in systems by involving certain sensors on the system. So in a dynamical system, you will have various sensors. One of them could be a relative displacement sensor. It's measuring with respect to the tortoise, how far am I, already on the race path, right? So that's a relative displacement sensor that is being used over there. Then it thinks of resting, not a right decision to take at the once we look at from the rear view mirror, but at that point in time the hare thought that was the right thing to do, thinks of resting. So essentially there is a lethargy that is coming in, and lethargy, or what we in the Indian terminology call as tamas, that is essentially setting up, and that is, tamas is a word used for inertia as well. So it's essentially a resisting force. It's something that is making us not go on the path that we are capable of going. It's essentially trying to slow us down on that particular path. That's a resisting force, and more often than not it is actuated mentally, which is what happened in the case of the hare also. It's not that he was physically tired. It's not like he had to take a break because he is so tired running that distance. It was a easy peasy lemon squeezy kind of a race for him. He could run very, very easily and reach that spot, but still the overconfidence made him take rest. So that's essentially a mental kind of behavior, right? So that's actuated mentally, and this is something that's becoming very important as we are looking at self-driven cars, etc., and we are building in control systems into them in terms of how they're going to look at these overall scenarios and make decisions in terms of where they're going to stop, take a break, or maybe recharge themselves depending upon the battery state of charge, etc. So those are things that can be affected by these kinds of logic that you build into the whole system, right? Now the hare takes a break, which is essentially means in the dynamical system, like an aircraft, you operate the air brakes. For example, you have the spoilers. You can increase the drag levels by which the speed of the aircraft will come down, right? So you can take a brake, which essentially is the braking force. More commonly you see on land vehicles, where you actually apply the brakes on a car or two-wheeler in order to reduce the speed. And then of course it relaxes. Unlike the constraint that we saw earlier on, it was in the previous slide, this particular constraint that we are talking about is a constraint which is related to the motion. There are constraints which are related to the coordinates. For example, in this pendulum problem that I talked about, the way I'm demonstrating this, it's a planar pendulum. In other words, it's moving only within a plane. Where it could be a spherical pendulum which is moving in three-dimensional nature. So these two will be quite different. When it's planar, there's an additional constraint that it cannot move out of that particular plane, right? So those are the kind of motion constraints that are there in how the motion can take place, and that's an analogy we can see when the hare relaxes. Okay, now where the hare could have relaxed anywhere he wanted, but he chose to relax under the tree shade. It's a hot summer day, possibly under the tree shade. So essentially we're talking about a certain boundary condition, because that's going to eventually decide from a space-time perspective the initial condition for the remaining part of the race, what he had in his mind. He thought he is going to rest for a short time much before the tortoise reaches there, and then he's going to continue the race. But that will become the initial condition. He'll be so well rested that he could probably run even faster than he ran the first half of the race, right? So that's essentially a boundary condition that you're essentially setting up, or when you think of space-time as an integrated quantity, it could also be the initial condition. But it slumbered and slumbered longer than it needed to, and that's essentially your inertia taking over. The way we introduce inertia as a concept is, if you look at Newton's second law already, we have that built in. We were writing, remember, the equation in Newtonian as F is equal to ma. But the same equation can be written with ma taken to the left hand side, and then you have F minus ma equal to 0. Now you remember, this looks very similar to what you were solving in your statics problems, where you were saying that summation F equal to 0, right? You are summing all your forces and setting them equal to 0, and then you're solving for the unknown quantities in terms of the known quantities. Now what you're trying to do over here is, it really is not a 0 on the right hand side, but we are taking this ma to the left hand side, and we are introducing what we call as minus ma, the D'Alembert's force. And what was discussed by one of you in the morning is this is like a pseudostatic kind of a problem, or sometimes also called, as I mentioned in the morning, quasi-static or pseudostatic kind of a problem, right? So that's essentially what's happening. It's another way of looking at the Newton's first law, where you're focusing on not considering these two as two different kinds of entities, but ma also as a force. It's a fictitious force, it's imaginary, but essentially if you're taking that as an additional force that is on the system, then essentially all you're doing is solving the statics equation problem, which you're so very familiar with solving. Okay, it's just that one additional kind of force has been introduced, namely negative of mass into acceleration.
Does that mean all problems are technically quasi-static?
It can be posed in that way. So it's all a question of how you're posing it, right? So it's a question, that's why once again the observer becomes so very important. You as the observer or the analyst decides whether you want to keep your MA on the right hand side or whether you want to keep it on the left hand side. When you're keeping it on the right hand side, it appears like a totally different kind of problem. You're solving a dynamics problem. When you're bringing it here and treating this as just like any other force, then you're essentially solving a static problem, or more specifically a quasi-static problem.
Got it. So if it's like a plane that's in motion and then like the first part of the problem is about the force on the plane, but there's no acceleration, then that would be quasi-static. But if it's just about like a bouncing ball, then you can't say it's quasi-static just because it's on the earth and it's rotating. Right?
That's right. That's right. So there are two things to this. One is the body's motion. The other is the frame with respect to which you're seeing that whole thing. So based on that, you know whether something is quasi-static or it is a dynamic problem. But many a times, even truly dynamic problems, if portrayed appropriately with the observer, can become a quasi-static problem, which is what I'm saying is just in terms of where you put this particular new entity that you're dealing with, which you didn't deal with in statics course. Now you're dealing with that. So where you put it and how, what kind of color you give to it in terms of what kind of entity it is, whether you're talking of it as something which is to be determined, mass, acceleration, etc., or you're talking of it as a fictitious force and treating it as like any other force, then you end up with a quasi-static model. Right? Yeah. But the examples that you gave are really interesting because some are more amenable to be treated as a quasi-static problem than others. But in general, all of them can be treated as quasi-static if I want to, by using D'Alembert's approach. Any other questions? Okay. Now let's see that race continues. The episode 1 is continuing. The tortoise is plodding on steadily even while the hare is resting at that place. So that's essentially another form of inertia. Now we're talking of Newton's first law, where we also we were talking only about F equal to ma, which is the Newton's second law, which we were talking about, which is valid only in an inertial frame of reference, which does not exist, as I said. But even before that, Newton gave another law in the same Principia, which he published in 1687. Of course, the original was in Latin, which was eventually translated into English, just like this was originally in Sanskrit and translated into English. That was in Latin and later translated into English. Not very different, right? We say something we don't understand is Latin and Greek, so something like that, right? So now we're talking about the first law of motion. Can anybody state it? Not necessarily in the words that Newton stated it, but what you understand of it. Newton's first law of motion.
The object in motion stays in motion, the object at rest is at rest.
Absolutely.
No force
Little-
applied on it.
Exactly.
Stay
Yeah.
down.
So that's teamwork. I like it now. So you fill in for what somebody else has left out. So essentially you're saying that a body is in a state of rest or of uniform motion, that is means constant speed and constant direction, unless and until it's acted upon by an unbalanced external force. You could have external forces, but if they are balanced, then once again the speed doesn't change, So, and also you can think of the rest as a special case of uniform motion where the speed is 0, right? You're just saying speed is constant. That constant can be non-zero constant, or it could be a 0 constant, right? So both are actually essentially talking about the same thing with explicitly stating the special case, and that's what we are talking about here. The tortoise is neither accelerating nor decelerating, so he's just going on and on. Whereas the hare, for example, starting from 0, he went to 0 to probably whatever his max speed is with very quickly. In other words, a very quick very large acceleration that he had, and then a very large deceleration to just stop at a particular place in between. Whereas here you're talking of a steady motion over here, just like an aircraft which is in cruise mode, right? So tortoise plods on steadily. Here we're talking about the inertia. Again, uniform motion we're talking about over there, which means that he's keeping his speed constant. Then eventually, of course, because the hare is still sleeping, he overtakes the hare, which is kind of a transition in your solution process. So solution processes will sometimes have certain transitionary natures in between. You can qualify, for example, when you're dealing with, let's say, in a structural analysis, a stress strain curve, you're trying to plot, which you'll study in deformable bodies. Essentially, you are having a linear portion, a non-linear portion, which all of which might be elastic, and then an inelastic portion, from which if you unload, you will have a residual strain. But on the other hand, in the elastic portion, if you come back to 0. In other words, you come back to the original shape and size. So here we are talking about different portions in the same behavior. Here we are talking of, instead of stress versus strain, here we are talking of distance versus time, which is the plot that you're looking at, the slope of which is your speed, and the curvature of which is your acceleration, because your second derivative of the distance with respect to time gives you the magnitude of the acceleration. So that's what you're trying to take at, and that curve can have two entirely different kinds of shape, or the behavior or the trend that you're looking at. And where the trend changes is essentially a transition that is taking place over there, because we are talking of the relative motion between these two. Because what we are not interested in is the absolute motion of the hare or the absolute motion of the tortoise. It's the relative motion, because that's what the whole argument was, who is faster. I want to decide one with respect to the other. Then eventually the tortoise reaches the finishing line, so which is essentially the finishing kind of condition. And there's a very interesting numerical methodology which is used to solve a lot of problems, especially initial value problems, where you're talking about so-called shooting method. You want a certain final condition to be achieved. You know the initial condition, you know the governing equation. Then you try to, just like firing a gun. When you're firing a gun at a target, depending upon the angle of your gun, you're going to have various locations at which the bullet is going to strike on a particular wall, let's say. So then you essentially are trying to change this angle to suit a particular target that you want to hit, and then you identify that, right? So that's called the shooting method in numerical methodology, and that's something similar to what the tortoise was, totally focused on where this bullet wants to hit the target. Like that, the tortoise wants to reach the finishing line without being distracted by a tree which is offering nice shade and fruit, etc. It's not trying to take a break or a rest over there, just on and on, trying to reach the goal. Okay, and it emerges the undisputed champ, which means that there's no diciness in terms of maybe or yes or this or that. You very clearly see that the tortoise has reached the finish line and the hare is very far behind from the finish line. So it's an undisputed champ that you have. So essentially you're talking of what is known in the solution parlance as uniqueness. Okay, because some equations can have multiple solutions, and then you have to decide which of the solution is the appropriate one. For example, if you're taking the square root of a particular number, you know it's plus or minus, right? Square root of 4 is plus or minus 2, right? So then based on the other conditions of the problem, you tend to decide which one of them is right. So there you do not have a unique solution, whereas here you have a unique solution that you end up with. And this is true for a lot of variational problems, because what you're interested in is the global minima global stationary principle rather than local stationary principle, which can give you many local regions where a minima or maxima might be reached, but that's not the overall maximum or minimum. Sorry. So, of course, once this happens over a period of time, then the hare wakes up to realize the loss. Waking up is a physical phenomenon, but awakening is a much deeper phenomenon. It's happening not just at your physical level, but your emotional, intellectual, and so-called spiritual level as well. When you awaken to a particular thing that has happened in your life and you're trying to make corrections for it so that you can have an enhanced quality of life from various perspectives, and that's awakening rather than just waking up. So awakening to again, the word is carefully chosen there, to realize the loss. A realization, again a beautiful word in English, it's of course to find out the truth, but if you look at the actual word realize, which already gives you a hint that what you are looking at so far is unreal, imaginary things that you're dealing with, and now you have a reality check that is happening, and that's essentially the loss that was there. And that's in a numerical process, of course, you have an error function because your target was at the finishing line, but somewhere in between you found a wonderful tree and you rested there. So there's a huge error from where you ended up to where you were supposed to end up. So the primary takeaway from episode 1 is that the slow and steady wins the race, as our moral people wanted to teach us, but more importantly, it's what we call in our theoretical methodologies as the classical theory. Okay, so classical theories are things that make you understand things from a qualitative perspective, but don't really give you enough to be successful in life, because we know that if you're too slow, then however steady you are not able to achieve too much in life anyways, right? So you have to enhance the other qualities as well, not just steadiness, not your stability alone, right? For example, in an aircraft, coming back because it's an aerospace engineering course, if you build an aircraft which is highly stable, it will not be maneuverable. So you can't use it like a fighter aircraft, for example, where maneuvers are the most important things that it does. So you really want maneuverability when you want to even sacrifice a little bit of your steadiness or stability of various kinds, and that's essentially trying to make it suitable for what it is meant for, what it is being designed for. Okay, so that's the classical theory. When the classical theory makes you understand to a little bit, but it's not sufficient, you need to go beyond that, which is where the, of course, this is the popular version that you see. And if you look at from a dynamics point of view, it's the classical theories which will be stated in pretty much all textbooks. So people stop here, which is why very few people, I don't blame the 8 of you, but very few people know about the 3 other episodes of Aesop's story. They only stop at slow and steady wins the race and they're done with it. In other words, in dynamics also, people are quite happy with the Newtonian mechanics solving this particular thing, and they stop with the classical theory. They don't go beyond it to understand the other nuances or subtleties involved in the problem, which is what the other 3 episodes bring to us, right? So next is, as I said, before we go to the second episode, this is just the first episode, which means it could be, for example, like most classical theories are linear theories, because that's the simplest problem to solve. Even if it's in reality non-linear, we assume it is linear, various parts of it, and therefore the so-called principle of superposition is valid. So you break the problem in a modular fashion into smaller problems, you solve each one of them independently, then you all put them all together like a khichdi, what we call in one of our dishes that you might be enjoying in your CVH, where everything is put into the same dish. So that kind of a thing. So essentially that's a linearized approximation which is possible only when principle of superposition is possible, which in turn is possible only because you have oversimplified the problem and neglected all the non-linearities that were there. Are there any questions so far before we move on to the second episode? Okay. So now before we get on to the second episode, obviously the hare is disappointed because he lost the race, knowing his capabilities, how fast he is, and how effortlessly he could have completed the race, because it was not so tough on him physically or even mentally. But then that's what we call as the lack of validation and verification. Now these are two terms unfortunately very interchangeably used by a lot of even advanced researchers, leave alone students. So it's something that I want you to learn upfront very quickly, because you do a verification when you have a reliable theory and you're coming up with a new theory or a numerical methodology or an algorithm, and you just compare with that theory, you do what is known as a verification. Like for example, there are two different approaches here. One is the Newtonian, the other is the D'Alembert's approach. Okay. Now I can cross-check these two to make sure that once I use the D'Alembert's, I am getting to the same result as I did with the Newtonian. That's essentially called as verification. It's not validation. Okay, it's a verification that you're doing of one theory with respect to another theory, or one numerical methodology with another numerical methodology, or one numerical methodology with another theory. These kinds of things, everything on paper, on book, or on a computer, you're trying to do. It's not the actual real life objects that are experiencing this. Then you're essentially talking about comparing with something that is a benchmark or something that you trust more. Let's say you trust Newton more than D'Alembert, then you keep that as the benchmark and you do the D'Alembert's way and then compare with the results you are getting with Newton, and you say it's fine. This becomes a little more non-trivial when you go to Eulerian, Lagrangian, because these are talking about work energy kind of methods where we are doing it in a little more different way. Here it's just a question of putting your right hand side on left hand side and treating it as another force and doing it. It's not, when we see it now, we'll think of it as a trivial continuation or extrapolation of this. But this actually helps in so many different ways in solving certain problems which otherwise look very complicated over here. So I'm not trying to trivialize D'Alembert, but compared to what Euler and Lagrange did with the work energy, or what the people did with the impulse momentum, etc., this is a much simpler transformation that you're having by just putting the right hand side on your left hand side with a negative sign, right? But you could solve the same problem, let's say once again going back to the pendulum problem or spring mass dashpot problem, all these kinds of problems you could solve using these methodologies as well, and then compare with this. That's essentially again a verification, because one theory with respect to another theory, or one numerical approach with respect to another numerical approach. But what is validation is comparing with the reality. That reality could be, like in the case of our aerospace engineers, a flight test. On the aircraft there are lots of sensors which can gather data. You collect all that data and you do an analysis of the data, and then you compare with whatever theoretical results you have got. Are you able to agree with that? That is essentially one level of validation. But that's a little more costly way of validation, because a flight test is quite expensive, but it has to be done for certain certifying requirements, etc. So it is done over there. The other way of validating is with experimental results in the laboratory. So you're simulating that actual real life, whatever is happening in the lab by using a specimen. For example, you could put that same aircraft model in a wind tunnel, some of which you have seen in IISc and many of which you have seen in other places as well, including Georgia Tech. So there you are essentially looking at comparing what you're doing numerically or theoretically or analytically with something that is actual physical model or a physical structure or the real life structure. Then you're doing what is known as a validation. So keep this in mind. So more often than not, most people only end up with verification because they're not doing actual physical experiments, but many cases it's required to go beyond that and do your validation as well. Now this disappointed hare obviously does some soul searching. Why this happened? Why did it lose the race? And that's essentially what we call as, in the dynamics parlance, analysis. You're doing an analysis to understand whatever has already happened. You're trying to take all of the information from that and analyze that data to get some inferences which can be takeaways for how you want to conduct your life or the experiment or dynamics in an appropriate way in the future, right? So what happens because of this analysis, because of the soul searching? Identifies the cause of the loss. Okay, why did it lose? The cause of the loss is laxity, lethargy, laziness, indolence, all kinds of things which are essentially talking about the tamasic guna that we just mentioned. It's essentially what you're doing is so-called invalid assumptions. What did it assume? It assumed that it could wake up on time and still win the race because the tortoise was walking so slowly, right? So that's an invalid assumption that he made about his ability to wake up on time without an alarm, of course. The challenge that he puts up for the tortoise is to go for a second race, which is essentially a second rerun of the entire problem, which is your second iteration. Remember, for the first one we had to have a initial guess or an assumption. Now we already have certain data in place. Now we want to improvise on that. You're going into the second iteration over there. The tortoise agrees, and that's essentially you setting up what is called as the inertial reference frame, because remember, a race is always one with respect to the other. So as I said, there's no such thing in reality as an inertial frame of reference, but the tortoise can be used as an inertial frame of reference because remember, it's not accelerating at all. It's just traveling at a steady speed, and anything that is not accelerating, because either its speed and or the direction is not changing, then because of its steadiness and because of its non-accelerating nature, essentially it's almost like an inertial frame of reference. Either you can fix that to the earth or you can fix that to the tortoise. Doesn't make too much of a difference. This time, of course, the hare gives it all to the finish, start to finish, and that's essentially if you want to track the hare, you're having what is so-called body fixed frame of reference. Remember, we introduced in the morning session an aircraft fixed frame of reference, a earth fixed frame of reference. Here we are talking of a tortoise fixed frame of reference and a hare fixed frame of reference. One is almost like an inertial frame of reference because it's not accelerating. The other is accelerating, especially at the beginning, by a huge amount, and then once it reaches close to the finish line, it's decelerating by a huge value magnitude, though it is negative of course in terms of the algebraic nature. So that's essentially a body fixed frame of reference, and you're looking at one's motion with respect to the other. This time it runs non-stop from the start to the finish without taking a break at the shady tree that was in between. So that's essentially validation, because now you're not doing it on any paper or theory or a computer or a calculator. You're essentially doing it on the physical thing, which actually, instead of a flight test, you have a on-ground running test that you're having start to finish, and therefore there's a validation of its capabilities. The hare knew its capabilities all the time, but just that it was not putting it to full use in the first episode. Now it does, and therefore wins by a big margin, which essentially is your verification of what you already know. From a theoretical perspective, you knew that capability was there. So when you're comparing with your theoretical capability, it's a verification. When it actually happens and you finish it, it's a validation. So essentially, this is a case where both are combining into the same problem, verification and validation. Most dynamics problems, these will be two separate things. One is a comparison with a theoretical model, the other is with a theoretical or computational model, and the other is with the actual experimental or flight testing. So the second episode's takeaway is not slow, but fast, consistent and reliable. Okay, that's the one which will win the race, and amongst the others which are either slow or inconsistent or unreliable, and that's these are the three qualities that come to the fore over here, and that's what we call as, remember the first episode we called it the zeroth order approximation, or the what we call as the classical approximation. Now we are talking about an improved version of that. Instead of slow and steady, we are talking of fast, consistent and reliable. It's essentially a first order approximation that you're going towards what could be successful in life. And that's obviously better than what we already had, the classical approximation, also called as the zeroth order approximation. So they didn't stop there, right? So they went on to the third episode, where we get on to from the 0 to first to now second order approximation, even better, still as individuals, not as a team. Okay, that's what episode 3 is all about, just that you're changing the path, right? How does it happen? The previous episode happened because the hare went into a mode of reflection, and remember, I talked to you about the Indian process of learning, Shravana, Manana, Nitidhyasana, listening, reflecting, and applying, right? So this reflection process is what gives rise to episode 2 and episode 3. Episode 2, because the hare went into a reflection mode, why he lost. Now the tortoise goes into a reflection mode, why did he lose the race in the second episode. And therefore that's what we call as you have a set of data coming from your run that you have done, and that's something that you have to post process. The post processing of the results gives you important information or takeaways from the whole whatever work you have done, right? Now once this reflection is done, there's a perception. So this is the most important thing. It's all about perception, how you perceive things, okay? That can completely alter in the further trajectory of where the story is going, or where the dynamic model is going, or where the reality that particular model represents, where it is going. All of that happens there. So it's essentially an inference that you get, a perception that you get once you do this reflection. So once again, the same color code remains. The yellowish green represents the actual story that we are talking about. The red, of course, represents the takeaways for dynamics that we are talking about, which is what I want you to focus on from your assignment point of view, right? So perceives that the victory is impossible with a race. The way it is structured right now, it is so very difficult to beat the hare unless the hare is giving up like it did in the first episode, right? So or giving up consciously or unconsciously because of its habitual nature to take a nap, possibly, right? So that's what you talk about when you're doing a dynamic analysis. You get a set of results. It's not that you're done with the problem. There has to be takeaways from that, okay? So there's the results, and there's a discussion over the results, and then there are the takeaways from that discussion, okay? So this is the results discussion portion. In the current format, the way the race is structured, just over land, then the hare is always going to win it by a huge margin, okay? No doubts about it. So the formulation is erroneous because the current format is not taking advantage of everything in your system. And this is very, very important in aerospace engineering because there are so many subsystems which go into the making of an aircraft. If one of the subsystems is underperforming, you're essentially carrying pretty much dead weight or a huge weight penalty because of that, which means that the overall performance of the aircraft is going to be reduced. Either its range is going to be reduced, or its speed is going to be reduced, or its payload carrying capability is reduced. So you want everything in the system to be working, all the subsystems to be working at their peak, so that you make sure that you're having a very efficient system overall, okay? So that's the erroneous formulation that is discovered. In other words, the design of the race path in our story. So we go on to challenges. So the tortoise goes on to challenge the hare to a third race, and this is obviously you're going for a next higher order approximation to the problem than what you already had, namely the 0th and the first approximations. You're going to the second approximation, right? So on the modified route, which is essentially a perturbation over the existing route. So you already have a particular route on the land from the starting line to the finish line with a tree in between. Then you're looking at extending that route beyond that, which is essentially a perturbation that you're giving to make sure that you have a more dependable, more reliable solution for your problem, right? So the hare, of course, is sportive enough and accepts the challenge posed by the tortoise, and that's essentially what we call as in the dynamics or most solution methodologies an admissible function, okay? So this admissible function is now accepted. It's committed to consistent speed, and once again here we're talking about all the rules are my rules. Wherever I go, whatever situation I'm in, whichever institution or nation I'm in, I make the rules as my own rules. Okay, so that way you are now not thinking of life as a burden or a drudgery. You're thinking of it as a game, and when you have a game, you obviously don't want to keep playing the same level of the game. You want to go to the next level, which is obviously more and more challenging, right? So you want to take up those challenges and make life more fun, make it a game, make it a play, and that's essentially what we are talking about. And that's possible only when the candidate involved is sportive enough, right? So the hare is sportive and therefore committed to the consistent speed that he is capable of. So he says, okay, it's your rule, but it's for our race, then therefore I accept it. So all rules are my rules as well. It's not just your rule or the rule of the game, but it's my rule. I accept it. It's like saying when you're playing football, you don't want to use the rules of cricket, right? So in cricket, you can catch the ball. In soccer, if you try to catch the ball, it's a penalty, or you have to be throwing it in, right? So depending on the game, you have to bring in the rules and obviously follow those rules. Otherwise, it's no fun either for the players or for the audience. So what does the hare do? It takes off and runs at top speed like it always did. And that in the aircraft parlance, we talk about the takeoff speed, and then reaching your maximum speed after you reach the cruise altitude or whatever altitude at which maximum velocity is the design velocity for that particular aircraft, right? And it reaches, of course, it wasn't aware of this, but the tortoise had set an extra path which is going across the river, right? So it reaches the broad river en route and possibly deep as well. And so you have an off-design condition. In other words, the hare is designed as a structure, as a body for a particular purpose. It can race through land very easily, but the same cannot be doing it. It's like amphibious aircraft can do it both on land and air and on water, but if you take any other aircraft on water, it's going to be perhaps a disastrous crash, right? So that's essentially what is designed. And it is designed for, and what we perceive as an off-design condition. And